This is the Lennard-Jones potential. This graph is a product of this relation here, known perhaps unsurprisingly as the Lennard-Jones potential function. It's a simple yet powerful mathematical model of how neutral atoms and molecules interact with one another, with interatomic potential energy on the y-axis and displacement between the two atoms and molecules on the x. This part of the function corresponds to the repulsive region on the graph. It's governed by the Pauli exclusion principle, and this part of the function corresponds to the attractive region of the graph. And it's governed by the van der Waals force, which is a comparatively weak electrostatic force. So, we have a repulsive region, and we have an attractive region. This seems like a perfect recipe for oscillations, and that's what we get. What you're seeing here is a graphical representation of the oscillations of different pairs of neutral atoms bound in a Lennard-Jones potential. We can clearly see that the equilibrium position here is the point where the Pauli exclusion principle dominates the van der Waals force for displacements less than the equilibrium position, and the converse is true for the displacements greater than the equilibrium position. The sigma term of the Lennard-Jones potential represents the distance at which the intermolecular potential energy between the two particles is zero. It's a measure of the size of the particles or molecules and is often referred to as the hard sphere diameter. The epsilon term is the minimum potential, known as the potential well, of a given Lennard-Jones governed interaction. Notice this motion is not simple harmonic, since the restoring force is not proportional to the displacement from the equilibrium position. We can see how, due to the Pauli exclusion principle, when the separation distance is less than sigma, the potential is greater than zero and it exceeds the asymptotic van der Waals force, and the atoms will never meet again.